We're talking about solving equations this period. Solving exponential equations. So what is an exponential equation? Well, it's an equation that has exponentials on either one or two sides of the equation, right? So for example, 7 to the x equals 9. That's an exponential equation. Or if you have 3 to the x equals 4 to the x, that's an exponential equation, right? So you could either have an exponential on one or two sides of the equation. All right.
How is that possible if x equals the same thing?
Right, well, it could be something else. But okay, so now, how do we solve these? So if you have one that looks like this, 3 to the x equal to 3 to the power of 5, let's say, right? As long as the bases on either side are identical, then their exponents will be equal to each other. So you could just set the exponents equal to each other. Okay? All right. So the goal then is to make sure that on either side of the equation, your bases are identical to each other. All right, so let's do that here. All right, on the first hand, I have 3 to the x, and then I have 9 to the 4, right? So my base here is 3, and here the base is 9. Well, how can I make both bases equal to each other? Well, okay, so what we want to do is it's easier to convert the bigger into the smaller. So it's easier to always write them in terms of their most elemental base, right? So 3 is as simplified as it'll get. So I'm going to leave that as is, 3 to the power of x equal to, now what about this 9? Is there any way I can write the 9 in terms of this base, 3 to the power of something? It's 3 squared, right? So, and you always want to do it in terms of exponents. So not 3 times 3, but it's got to be 3 times 3 to the power of something. So I could just rewrite the 9 as 3 squared, and this whole thing to the power of 4, right? So what I have here is 3 to the x equal to 3 to the 8, and then what do I do to the exponents? Once the bases are the same, the exponents are the same, so x is equal to 8. All right, so what did we do? We wrote the bigger one. We try to convert all of them into the most elemental form of the base. Okay? All right. This next one here, I have 2 to the 5x. Now 2 is as simplified as it's going to get, so I'm just going to leave it as is. Equal to, well, what about the 4? Can I rewrite the 4 in terms of 2 to the power of something? It's 2 squared times 2x minus 1. All right, so some common mistakes. Right, we are. So to avoid some common mistakes, leave exponents as exponents, leave coefficients as coefficients, bases as bases, right? If you swap their places, then you're changing the problem. All right, so now I'm going to set the exponents equal to each other, meaning 5x is equal to 2x minus 1. So 5x is 4x minus 2. That means x is equal to negative 2. Okay? Yeah.
And then 2x to 2 to 5x becomes
2 to the 5x stayed 2 to the 5x. And the other one, where it was a 4, it became 2 squared. So
how did that become on the next line? How did that?
So 2 to the 5x stayed 2 to the 5x.
Yeah.
The 4 changed to 2 squared.
And then on the next line.
And when the bases are the same, you just set the exponents equal to each other.
Oh, okay.
All right.
Yeah.
Right. I subtracted. Okay. Yeah.
Real quick, you see on the first one you did, you put it like 3 squared and then parentheses and the 4.
Yeah.
Why didn't you do that for this one? Where it's like 2 squared and then parentheses 2x minus 1.
I did though. I did 2 squared and parentheses 2x minus 1 here. Oh, why didn't I put the big part? That's just form. You can or you don't have to. Okay? I could have easily written that as 3 squared times 4 and it would have been the same. Okay? No, remember these are exponentials, and what's the domain for exponential functions? All real. So, you know, if you did it correctly, it's going to work out. All right. Now, let's do D before we do C. So, I have a 9 and an 81. Now, you can change the 9 to 3 squared, but you don't really have to, right? Right. So I can leave the 9 as is. And what happens to the 81? It's 9 squared. Now that the bases are the same, I can set the exponents equal to each other. 2x is equal to 3x, I'm sorry, just 2 is equal to 3x plus 2. You subtract 2's, so 0 equals 3x, and how much is x? X is 0, right? And if you do a quick mental check, if I put x equals 0 into here, I get 9 squared, which is 81. Okay, now, okay, here's the next one. Here's C. I have 1/2 and I have 8. Now, before you start taking out your calculators, okay, I have 1/2 and I have 8. So here's what I do. 1 is a fraction, 1 is a whole number. Okay? Now, I want to convert. First, let's just look at the 2 and the 8. Let's forget about, you know, the fraction and the whole number. How do you go back and forth between 2 and 8? 8 is really what? 8 is really 2 cubed. 8 is really 2 cubed. So 2 cubed is equal to 8. Well, that's fine, but here I have a 1/2, right? Well, what if I have 1/2? What can I raise that to in order to get an 8? Okay, so here's a little exercise then. All right. What's 2 to the 1? 2. What's 2 squared? 4. What's 2 cubed? 8. Now, what's 2 to the minus 1? 1/2 to the 1, which is 1/2. What's 2 to the minus 2? 1/4. What's 2 to the minus 3? 1/8. Now, let's do this. What's 1/2 to the 1? The 1 belongs to both of these, so it's 1/2. What's 1/2 squared? 1/4. What's 1/2 cubed? 1/8. Okay. What's 1/2 to the power of minus 1? 2. Right, it's just 2. What's 1/2 to the power of minus 2? You flip. 2 squared is 4. What's 1/2 to the minus 3? 8. So do you see that? So what's the key then for the exponent? What do you have to make the exponent to go between a whole number and a fraction? A negative, right? So now I have to go between a 1/2 and an 8, right? So this is the 1/2 is it's in its most elemental form. I leave it as 1/2 equal to. Now I need to change this 8. All right, so here's how I would do it. I'm not going to go through this whole thing each and every single time. Here is how I, Miss Malikian, do it at this age as a math teacher. Okay, to go between a 2 and an 8, it's 2 cubed, right? Now, if one is a fraction and one is a whole number, then I have to do a negative exponent, right? So now, I need to get the 8 to be the same base as my first one. So 1/2 to the power of negative 3 is 2x plus 1. All right, so that's how I rewrite it. So now what am I going to do? Set the exponents equal to each other. Negative 6x minus 3, I just distributed here. Okay, I'm going to do a couple more examples of this. Now, I add 6x to both sides. 10x plus 1 is equal to negative 3. 10x is equal to negative 4. And what's x? Negative 4 over 10, which is negative 2 over 5. So now, let's do a couple more examples here. All right? So, 1. So suppose I have 1 over 3 to the power of x equal to 9 to the power of 2x. How am I going to rewrite these? 1 over 3 to the power of x is equal to 1 over 3 to the power, well, wait, now how do I get the 1 over 3 to be a 9? Negative 2 times 2x. Okay, so what I'm going to do now is I need you guys to write this down. I'm going to put a couple of these on the board, and I want you guys to be, to just rewrite them. Don't solve them, just rewrite them, okay? All right, so let's do this. Huh? Yeah. Yeah. All right. Right, so for the first one, I'm going to have 1/4 to the power of x equal to what? 1/4 to the power of negative 2 times 2x. All right, what about for the next one? 1/2 to the power of 2x equal to 1/2 to the power of negative 4 times x. And the last one? 1 over 3 to the power of negative 3x is equal to 1 over 3 to the power of x plus 1. Okay? All right. So just figure out the number first and then add a negative to the exponent when you have to flip one of them and make it a fraction.
We should always make it a fraction of the big variable.
If you can, it's fine. It's usually, well, but then you're going to have a fractional exponent. This is usually the easier way to do it. Okay. Now, what if you're given some information, like in real life, and you want to, in a real life setting, and you want to write an exponential function to model the setting. So remember when we first talked about 7.1, I gave you guys a couple of examples about where exponential functions are used. And actually, they're used in so many places. Like if I think of exponential functions, so many things run to my mind, right? There are so many places where it's used. But what you do is you take the real life situation and now you have to write an equation to model it. And so many real life situations are modeled using exponential functions. So how do we write an exponential function? So first and foremost, the general form of an exponential function is this. It's y equals a b to the x. Now, how do you write an exponential function? Substitute the given information into this formula. Now let's just do a little bit of a background as to what this formula is, all right? Now, usually in this real life situation, there's going to be some sort of a change, right? You had a quantity and now you have a new quantity. So the original and the new amount, all right? Well, both of these are represented here. The y happens to be the original amount. The a is the initial amount. I'm sorry. Oh, I'm sorry, I did that wrong. I'm sorry. No. Okay. The a is the original amount. Oh my, that's a first. Write that down. Today is what? 2/13. Okay, today is the day I messed up the original and the final amounts. Write that down. Okay. So if A is if A is the original amount, what's Y then? The final amount, right? Or the final amount. Now, so things are changing, right? And everything, each situation is different in that things change at a different rate. Okay? So this will give you information on, this is a constant, and it tells you how fast the quantity is changing. So how the quantity changes. And X is going to be your time. Okay? So what we're going to do is we're going to substitute the given information. We're going to solve for B. And then we're going to substitute B back into the equation, but this time leaving X and Y as the variables. All right, so let's do one and we'll see. All right, so Kristen is doing an experiment, and she starts an experiment with 7,500 bacteria cells. Okay? After 4 hours, there are 23,000 cells. All right? So it says to write an exponential function that could be used to model the number of bacteria after X hours. So the equation we're going to write is y equals a b to the x, right? Now remember, we had an initial amount that goes into this, and we have a final amount that goes into this. All right, so in the problem, what am I given? What is this? 7,500. Which quantity is that? That's your A, right? Because that's the initial amount. So A is 7,500. What's 23,000? Y. All right, so what we're going to do is write this stuff in here. So 23,000 equals to 7,500. And do we have any other information given? What about this? After 4 hours, you have 23,000 left. So what's 4? That's your X, okay? In this case, it's the time. So after 4 hours, that's your X.
What about the B?
Okay, well, we're going to solve for the B now.
Isn't it just 22,000 minus?
So X is, okay, so here's what we're going to do. I have 7,500 times B to the 4. Okay, so you divide. So this cancels, first of all, and whenever you have something with zeros divided by something with zeros, you could cancel an equal amount of zeros. It just gives you smaller numbers to work with. So let's plug this in, and I'm going to show you how we're going to do this. Please take out your calculators. I need you guys to follow this with me. Okay, so here I have 230 over 75. And that's 3.0667 equal to b to the 4. Now, I just write that number as a placeholder for me. I'm not really going to type that number in ever. All right, now, how am I going to solve for b? If b to the 4 equals this, what do I do? The 4th root of this and the 4th root of this. So that'll give me an expression for b. So now going back to your calculator, here's what you're going to do. 4th root is 4 math, and it's that 5th option. Now, I'm not going to type in 3.066666 because that'll give me a rounding error, especially with exponential functions. You might think you're not going to get an answer that's really off, but man, will you get an answer that's really off. So we do second answer. Okay? So it's second and that negative symbol. What that does is it just inputs the last answer automatically, and when you press enter, that's what we get. Okay? Right, so it reduces the what do you call it? The error all around. So what we're gonna do, this is B. This is a constant particular to this problem. It's sort of like the rate of how fast this is changing. We normally go to 4 decimal places. So it's gonna be 1.3233. That's my B. All right. Now, remember what the last part of the process was? Is to substitute B into the main equation. So I'm going to rewrite the main equation, y equals a b to the x. Now, I put in a, I put in b, but x and y have to stay variables. So y equals 7,500, 1.3233 to the power of x. Okay? And that's it. That's the model for this.
The answer is not what equals to the answer.
The model is, yeah, the answer is the actual equation. Now, the next part of this is how many bacteria cells can be expected in the sample after 12 hours? So which one of the variables here is time? X. So, right. So when x is 12, how much is y? And we said that y was 7,500 times 1.3233 to the power of 12. So this is 7,500 times 1.3233 to the power of 12. Enter. Okay, here we go. So this is 216,252. Now, I'm not going to tell you how to round or to what place to round for this particular problem, because you need to know that if you're talking about bacteria or any other type of population, you can't have 0.43 of a bacterium, right? Or you can't have 0.43 of a wolf if it's a wolf population. So you have to round to the nearest whole number. That means this many bacteria. In your answer that you put on the answer space, I'm also going to look for units. So it's 216,252 what? Well, it's bacteria. Don't just leave it as the number. You have to specify what it is that that number describes. Okay? So again, I'm not going to ask you to round to the nearest whole number. It's on you to remember. Okay? Yeah.
I got somehow to 216,302.
I got 302.
Multiply.
Okay, so let me, so did you put in your parentheses exactly?
Yeah, one.
Okay.
I have more numbers though.
I'm gonna take one of them out. Okay, so if you put in a different value than I did, then that would give you a different answer.
No, but I just put in a more like
Right.
because I just have more digits.
Right, and you, right, so we are all gonna be working with the same number of digits, because this is what I mean. If you're, the difference in rounding will make huge differences in your answer. So we're all gonna agree for B, and I'm like on the test I will have specified. For B, we're all gonna round to the 4th decimal place, and you're gonna round properly, correctly, and then everybody will have the same answer. Okay, that's important, because then, like if you're talking about a population in a city, you'll be off by like 300 million people, and that's a significant difference, right? All right, let's do this next one. Another place where we use exponential functions is in compound interest. So compound interest is if you have money in a bank, right? And in a savings account, and the bank pays you interest, right? So suppose you open up your bank account and there are $10,000 in there. On the first round, when you get your statement, you would have gained some interest, right? So suppose now you have $10,100 for the sake of simplicity. Now when the bank is going to pay you interest again, they pay you on that full amount, 10,100, not the original 10,000. This is compound interest, that every time you're getting paid on the new dollar amount, and so on. A couple of other things also factor into this, and that's based on the type of account or based on how the bank runs their accounts. It could be that, you get a statement every month, meaning the bank pays you interest every single month. You might get a statement once every 3 months, right? So 4 times a year, or twice a year, or 3 times a year, and so on. So that factors into how much money you're going to get at the end of the term. All right, so the formula is this. Now, before you ask your question, I'll answer your question. You do have to memorize all these formulas, okay? All right, A, again, this is the final balance. Okay, P is called principal, and that's not Miss Howard, that's the money that you deposited when you opened up your account, okay?
Is that like first of all?
Yeah, what's R? Rate, and how do you put in the rate? As a percentage or as a decimal? As a decimal. T is time, it's the number of years. Now here's the important one. This is the new one. N. N is the number of times a year the bank pays you interest. So if you get a statement 3 times a year, what's N? 3. Okay, so N is the number of times per year, that the bank pays you. Say that again? Yeah.
Why is that longer?
Huh?
Why does it have to be 1 plus that?
Oh,
What is the 1 after?
1.
I know it. It's 1.
yeah.
We have that 1.
That's the growth rate. Okay, so we're gonna actually look at because 1 plus 1 over n over to the power of n. This is a quantity, like it falls out of the math equations, and that's a lovely quantity that, yeah. Okay. So if the bank pays you interest annually, what's n? How much is n?
1.
1, right? What if the bank pays you monthly? What's n? Quarterly, what's n?
4.
Right? So it's the number of times a year. All right, so let's do this one. A sum of $8,000 is deposited into account with 5% interest. Okay.
No, it's not.
Yeah, hold on. Okay. If the bank pays you interest quarterly, then n is 4 because there are 4 quarters in a year. Okay, that's not we're not doing that. Okay? Now find the balance in the account after 15 years. If the interest is compounded, and we have 3 situations here: semi-annually, monthly, daily. All right, so let's just write down, the blanket given here. What's $8,000? What variable is the $8,000? P. Interest is 5%, but it's going to go in as 0.05. This is where the majority of the mistakes in this problem will be. All right, is people either forget to convert or they convert to the wrong amount. You have to divide by 100, so think of it as dividing by 100. Think of it as moving the decimal point to the right, to the left twice, whatever. Just get to the right answer. All right. If you have any questions on that, come to bonus. This is not an Algebra 2 topic, so I don't want to spend too much time on converting to decimals. All right. Time is 15 years. So the first case is the bank is paying you interest twice a year, semi-annually, twice a year. So n is equal to 2. All right, so we're going to put it in the formula. A equals P 1 plus R over N to the power of NT. So A is equal to 8,000. 1 plus, the rate is 0.05. over n was 2 to the power of 2 times 15. All right, so have your graphing calculators out. At this stage in Algebra 2, I would like for you to be able to put this entire thing in your calculator in one shot, no rounding in intermediate steps, and then everybody is going to get the same exact answer magically. All right? So, $8,000, 1 plus 0.05 over 2 to the power of 2 times 15. You can do that in your head, 30, or I'll just show you that you could put it in as an expression, 2 times 15. Enter. You have $16,780 and what? And 54 cents. So A is equal to $16,780 and 54 cents. Now, again, I'm not going to tell you to round to 2 decimal places. You need to know that you're supposed to round to 2 decimal places because we're talking about money. And money, currency, is always given in dollars and cents to 2 decimal places. And you need a dollar sign in front of it because those are the units. That is the unit for this. So that's this one. Okay, yes.
Wouldn't you put parentheses around 0.5 divided by 2?
You don't have to.
Why would you do that?
You don't have to. Yeah, it knows. It's smart. It knows. Okay? All right. So for the next one, interest is being compounded monthly. So A is 8,000, 1 plus 0.05 over what? If it's monthly, how much is N? 12. Over 12 to the power of 12 times 15. Now, in these problems, don't type this all over again, right? So I do second enter and it gives me back the last expression I put down, and all I have to do now is to edit this. So it's going to be 12 times 15. In here, it's 1 plus 0.05 over 12. So what I do is type in the 1, and now to insert another character, second, insert, 2, enter. All right? Okay, so now we get $16,909.63. Okay? Now, first the bank was paying you twice a year. Now they paid you 12 times a year. So look at how much more money we got, guys. It was $16,780. Now we have $909 over the 15 years, right? So that's like $100 and some over the 15 years. Now, yeah, I'm going to do it one more time now. Okay, I'm going to do it one more time. So now the bank is paying us daily. Okay, so every single day the bank is paying you interest. We are going to make so much money. How much is N? 365. So let's put that in. I want everybody to plug it in before you call out answers. So don't call out any answers just yet. So this is going to be over 365 to the power of 365 times 15. Okay, here we go. Second, enter. Okay, that gives you the last equation you put in. So all you have to do is go in and edit. Now, I had a 12 in here, but I need a 365. So here we go. 3, 6. I need to input another character. So I do second, insert, 5. Now I have a 365 in there. 3, 6, and I need to put in another character, 365. So I want you guys to be able to use all of the features on your calculator, right? This is why you have this. All right. Enter. Let's see how much additional money we're making. Oh my goodness. Look at that. Over the 15 years, Rather than making 909, it's now 935. So it's like 20, yeah, 26 extra dollars. $1,935.13. 16,000. Okay. So there we go. Yes.
So why are you having those